In this section, we're going to look at the idea of partial fractions. Now, partial fractions aren't explicitly to use in the context of integration, but we can use partial fractions very well in the context of integration. So we're going to look at the idea of partial fractions in the context of integration. So we want to start with what we know. And what we know is how to integrate things like u to the nth power, or 1 over u, or 1 over u to the nth power if u is linear. So we know the technique to do that. So u to the nth, we take and raise the exponent by 1, and then have a coefficient of 1 over n plus 1. Let me just write that down. So we get 1 over n plus 1 times u to the n plus 1 power. And then obviously tack on a plus c. And then if we were to integrate 1 over u with respect to u, that would be the natural log of u, again, plus c. And if we were to integrate 1 over u to the nth power, I'd probably think of that as u to the negative nth power and do the same thing as I did above. So add 1 to the exponent, we get an exponent of negative n plus 1, and then divide by that as the coefficient, 1 over negative n plus 1, and then tack on a plus c. Now, one thing I do want to mention is I use the variable u in these cases. And if you were to do this with any linear piece that acts like a linear u, let's take 1 over 4x minus 9, for instance, integrate that with respect to x. That's linear. And so that's going to be natural log of 4x minus 9. And then because we have that 4 out front, we would divide by a 4. Okay. So if we have coefficient of 4, we divide by a 4. If we would have had a coefficient of, let's say, 7, if it was 7x minus 9, I would have had to divide by a 7. Okay. And then obviously at the end, we have to tack on our plus c. But that's the idea. So we know how to do this with u to the nth power as long as we have a linear piece. And then if it is linear piece, we can just quickly divide by the coefficient of x. And that's basically just a u substitution with this one. So we know how to quickly do integrations that look like this. So that's what we know. Now, the idea behind partial fractions is we're going to start with messy looking rational functions that we want to integrate. And then we're going to break those into nicer looking rational pieces. And those nicer looking rational pieces are going to look like u to the n, or 1 over u to the n, or 1 over u, where those u's are linear. Because then I know how to integrate. I know how to integrate these. So if I can sum up a bunch of nice things where these u's are linear, then we're good to go. Now, before we start doing breakdowns of fractions and messy looking rational functions, Let me start with just an integration with using basic rules. So we're going to integrate 3x to the fourth minus 4x plus 13 plus 7 over 5x plus 1. We're going to integrate that with respect to x. So this one is already set up in a way which coincides with these rules. Okay, so it's already set up in pieces that look like this. So I can go ahead and quickly find antiderivative here. We're going to get 3/5 x to the fifth. That's what happens when I raise the exponent on x by 1 and then divide by 5. Minus 4/2, which is better called 2x squared. I'll write that 4/2 as just being 2. Plus 13x plus, well, the 7 can be factored out, and then I'd take natural log of 5x plus 1, and then I'd divide by the coefficient of x, which is a 5, so I'd get 7 over 5 times the natural log of 5x plus 1. Again, that works just like any other thing with a linear piece in the argument. Just divide by that 5. So we're always dividing by the coefficient of x here. And there you go. So that is a very nice integration to do because it's all set up in pieces which I can integrate fairly nicely using the rules that we know. After we know how to do that, then it's a quick step to say, well, what if my fraction is not set up in ways where we can, in the pieces that divide nicely, put it that way. What if my rational expression that I'm trying to integrate is something like x squared plus 3x minus 7 divided by x plus 4? So I want to integrate that with respect to x. Well, the first thing we should notice is that the numerator has higher degree than the denominator. So this is polynomial divided by polynomial. The numerator is x squared plus 3x minus 7. The denominator is x plus 4. The numerator has higher degree than the denominator. So what I'm going to do is I am going to divide. So I'm going to do this off to the side. I'm going to take x squared plus 3x minus 7, and I'm going to use either long division or in this case I can use synthetic division to divide by x plus 4. Okay. Hopefully you've done either long division or synthetic division. If you haven't done those in a while, I guess let me refresh that idea. Now this is going to look a little bit goofy because they don't have a lot of nice division symbols in Microsoft Word, but there we go. So basically, we divide this. We put the denominator out front. We put what we're dividing underneath. I put it in a box here. Usually you just see line above that. So I asked myself, what do I need to multiply by x plus 4 to get an x squared. Well, I need to multiply by an x. So then I multiply that times an x plus 4. And I end up getting, oops, I went too far. I end up getting an x squared plus 4x. Now, I subtract that from this polynomial, and that is going to give me a new polynomial. The x squareds cancel each other out, and 3x minus 4x gives me a minus 1x, and then my minus 7 doesn't do anything. So we're dropping down again. Excuse the notation there, but basically we drop down and we get 3x minus 4x gives me minus 1x, minus 7, there's nothing to combine, gives me minus 7. And then I ask, well, what do I need to get to multiply by x plus 4 so that the lead term becomes a negative 1x? And that is simply minus 1. So an x minus 1 is what I have up here. When I multiply the minus 1 times x, I get minus 1x. And then when I multiply the minus 1 times the 4, I get minus 4. Remember, I'm going to write that right underneath, and then I'm going to subtract. And then after I subtract, I end up with negative 7, well, negative 1, that's going to be plus 1, negative 1x plus 1x cancels out. Negative 7, and that's going to be a plus 4, gives me a negative 3. So I end up with a remainder of negative 3. So that's how to use the long division in that case. I know, again, it's fairly messy looking how I've done it. But each one of these things, often you probably see a line under that, or whenever you subtract, line under that whenever you subtract, something of that nature. So the point is, let me actually make that a little bit, oh, didn't do that. So, weird. Okay, sorry. So anyways, the point is, we've done this, and that means that when you divide x squared plus 3x minus 7 by x plus 4, you get x minus 1 minus a fraction. Or you could also say plus a fraction. It doesn't matter how you do this. I said minus because I knew we had a negative 3 over x plus 4. That's what the remainder means, right? Is that if you have a remainder of negative 3, that's of lower degree than the x plus 4 you were dividing by. And so x minus 1 plus negative 3 over x plus 4 is the same thing as x squared plus 3x minus 7 divided by x plus 4. So that's what I do. I say, well, this integration is the same integration as x minus 1 plus a negative 3 over x plus 4. And now each of these terms, each of these 3 terms, matches up nicely with stuff I already know how to do. So while this fraction wasn't nice, not with my regular rules anyways. When I divided it, it became nice. So the antiderivative of x is 1/2 x squared. The antiderivative of -1 is just minus x. And then the antiderivative of -3 over x plus 4 is going to be a -3 times the natural log of x plus 4. Normally, I would divide by the coefficient of the x, but since the coefficient of the x is 1, 3 divided by 1 is just 1, so I'll just leave it as a 3, or leave it as a -3, in other words. So I took a messy looking rational function, I did some algebraic work to it, and I broke it down into nicer pieces to integrate. And those nicer pieces to integrate were very easy to integrate in this case. And so I just integrated them piece by piece. Again, some people would use absolute values around the argument inside the natural log. I'm using parentheses just for the sake of quickness. So there we go. And all that took us, all of the knowledge we needed is the knowledge of how to divide one polynomial by a polynomial of lower degree. By the way, we can't do anything here when I have -3 over x plus 4 because the polynomial of higher degree is in the denominator. That gives you a hint at how things are going to go. In example 1, we said if we had lots of different pieces that we could do individually, then we would do that. In example 2, we saw that if our numerator had larger degree than our denominator, then we can divide and break into nicer pieces. And we can always do that. If we have a rational expression where the numerator is of higher degree or equal degree than our denominator, then we can divide to create an expression with a polynomial piece out front plus a rational expression where the numerator is of lower degree than the denominator. Now, for this reason, for the next few examples, we're always going to start out where our denominator is of larger degree than our numerator. So we're going to have polynomial divided by polynomial. We're going to have a rational expression. And we're going to say the numerator has smaller degree. So we're always going to use those types of fractions because if I had ones where the numerator was of larger degree, I just divide out. Now, when our denominator is linear, then we use natural log. We integrate 1 over u. We get natural log of u. But what happens when our denominator is not linear? Well, when our denominator is not linear, we're going to use another algebraic tool, and this is the algebraic tool of partial fractions. We break down rational expressions into a bunch of smaller fractions, and those smaller fractions are going to have linear denominators. That's the goal anyways. We want to start with an ugly looking denominator and then break the expression down into nicer pieces to deal with. Now, when we do this, the algebraic work that we're going to do is not long division, but it is going to require factoring our denominator. It's going to force us to rewrite our one rational expression into a sum of smaller fractions. And then it's going to force us to find the individual numerators to make everything fit well, to make it all fit well or fit right. So let's do an example here. Let's integrate this rational expression using the tools of partial fractions. We're going to integrate the quantity x plus 1 divided by the quantity x squared plus 5x plus 6. So let me do that. In order to do this, we're going to have to factor the denominator. So we factor x squared plus 5x plus 6. Now, that actually factors into a pretty easy thing. Factors of 6 that add up to 5 are 2 and 3. So I would get x plus 2 multiplied times x plus 3 as that factor. Now that means I can take this rational expression, which has smaller degree in the numerator than denominator, and I'm going to write that as a sum of two fractions, one of which has x plus 2 in the denominator, and the other of which has x plus 3 in the denominator. And I just need to figure out what the numerator is. And it turns out if I am in this case where I have my denominator factoring into a product of distinct linear pieces, then I can know that the actual summation here will just have a real number over x plus 2 plus a different real number over x plus 3. And I'll call that a and b for now. So I know that this is going to be possible for some choice of a and some choice of b. So I just need to figure out what a and b are. What we would do is you would say, if this were possible, which it is, we know it is, then I could multiply both the top and the bottom by x plus 3 of this first fraction. Notice what I'm doing. I'm choosing x plus 3 because in this first fraction, the x plus 2 times the x plus 3 would give me this exact denominator. I'll do the same for the second fraction, and I'd say, well, what do I need to multiply x plus 3 by to get the common denominator of x plus 2 times x plus 3? The obvious answer is that I need to multiply x plus 2 on the top and bottom to get that. Now, all of the denominators now are the same after I multiply. X squared plus 5x plus 6 is equal to x plus 2 times x plus 3 is equal to x plus 3 times x plus 2. So that means my numerators have to be equal. The x plus 1 that I have on the left-hand side here has to be equal to a times x plus 3 plus b times x plus 2. So basically, if the fractions have the same denominators, then the numerators have to be equal. And this may not look like a lot, but it turns out this allows me to find the a and the b. because this is one equation and it actually can be rewritten as two equations. I'll show you how that works. Let's distribute the A and distribute the B. And normally how we rewrite it is this. Now, this actually gives me two different properties with the A and the B. So we're going to create two equations. So the first equation is the one that gives me the coefficient of x's. So the coefficient of x equation, on the left, the coefficient of x is 1. On the right, the coefficient of x is going to be a plus b. So a plus b together has to add to a 1. Now, the reason for that, the reason that the 1 and the 3a and the 2b aren't going to play into the coefficient of x is because we'd have to combine like terms, and the constants are not like terms with the x terms if I'm adding. And that gives me a hint at my second. Is the constant equations. So the constant equation, on the left I have also 1, just this one. But on the right I have 3a plus 2b. So I know that 3a plus 2b has to be equal to 1. This gives me a pair of linear equations that I can solve for a and b. Now, we can solve in a variety of different methods. One method is the elimination method. The elimination method would say, well, let's multiply this first equation by a -2. I get -2a minus 2b is equal to -2. The second equation, let's leave alone. That's 3a plus 2b equals 1. And then we add the two equations together. And when we add those two equations together, we end up with 1a is equal to -1. So a would be -1. Then I'd plug it in to one of these. Doesn't matter which one, which equation. If a is -1, then b has to be 2. So a is -1, b is 2. So that's one way. That's using the elimination method. You could have also, if you rather than use the elimination method, you could have utilized the substitution method. You could have said b is equal to 1 minus a by subtracting a from both sides of the first equation. And then in the second equation, you could have replaced the b with 1 minus a. When you do that, you'd get 3a plus 2 minus 2a equals 1. And subtracting 2 from both sides and combining like terms would give you a equals -1. And just as before, you'd plug that in. If a is -1, you plug it into the first equation or the second equation, you'd get b is 2. So a is -1, b is 2. Yet another way you could have done this is with technology. And I like to do this a lot with technology. It gives me a real quick, easy way to do it. What I mean by technology is I would create the augmented matrix. You may not have seen this technique, but I would create an augmented matrix with the coefficients. So coefficient of A is 1, coefficient of B is 1, is equal to 1. So I get 1, 1, 1. That represents my first equation. My second equation gives me 3, 2, 1. I have to line up the A's in column 1, the B's in column 2, and the constants in column 3 there. So A, B, constant would give you 3, 2, 1 as your second row of the augmented matrix. Whoops. And if you do something called taking a row reduced echelon form of that matrix, this is something that you can type into your calculator. I won't do that right now, but I will show you how to do that on like a separate video to do the RREF on your TI-84. What you're going to do is you're going to get a row reduced echelon form that is 1, 0, -1, and then 0, 1, 2. And so in augmented matrix world, that means that A plus 0B equals -1. In other words, A equals -1. And the second row now means B is equal to 2. And again, plugging those in, you'll figure out how it works, or you'll see that it works. Excuse me, you'll see that it works. So whichever method you use, whether it's substitution, whether it's elimination, whether it's using the row reduced echelon form of an augmented matrix, you end up with A is -1 and B is 2. That was the goal. Remember, we started with this trying to figure out what A and B were. Now I know that A is -1 and B is 2. That means my original integration, the one we started with, is the exact same integration as taking -1 over x plus 2 plus 2 over x plus 3. I think I'm going to rewrite that with the negative with the 1. There we go. So a over x plus 2 plus b over x plus 3. Now we know what the a and b are. And now we have this rational function, this rational expression, rewritten as being identical to one we can integrate nicely. So we can integrate both of these parts really nicely using natural logs. Again, I'm going to use parentheses around the argument. You may want to use absolute values around the argument. The antiderivative of -1 over x plus 2 is just -1 times the natural log x plus 2. The coefficient of x is 1, so we can divide by 1, doesn't do anything. When I factor the 2 out, I get 2 times natural log of x plus 3 as the antiderivative. Again, coefficient of x is 1, so when I divide by that coefficient, it doesn't change anything. So my final answer is that the antiderivative of quantity x plus 1 divided by the quantity x squared plus 5x plus 6 is equal to negative natural log of x plus 2 plus 2 times the natural log of x plus 3 plus any constant that we want to add. Again, this part is the quick part. The harder part is setting up this and solving for the a and the b. This in general is going to be how it works, although we're going to see what happens later. We're going to see what happens when our factoring isn't quite as nice. Let's try another example. Try this on your own if you'd like. I'll give a couple of seconds and then I will start this as well. So you can push pause on the video if you'd like to try this on your own. So as I do this, what I'm going to do is I'm going to first notice that degree of numerator is smaller than the degree of denominator. So I don't need to do any long division here. And therefore, I start by factoring the denominator. Now, x squared minus 8x plus 12. Factors of 12 that add to a negative 8 are negative 2 and negative 6. So if I take x minus 2 times x minus 8, that's going to give me x squared minus 8x plus 12. They are different factors. So since they're different factors, the way I'm going to set this up is I am going to take something, I'll call it a, over x minus 2, plus another thing, called it b, over an x minus 6. And I know that is going to have to equal 7 over x squared minus 8x plus 12. If you think about forcing common denominators, I would have to multiply the a over x minus 2 by x minus 6 divided by another copy of x minus 6. And to get common denominators in the second denominator, what I'd have to do is I'd have to multiply by x minus 2 over x minus 2. Now I have common denominators. Therefore, the numerators have to be equal. I'm going to set this up in one step. 7 is going to have to be equal to ax minus 6a. Plus bx minus 2b. Now, if I'm combining like terms, what's this mean for the x's? Well, the left-hand side, I have no x's. Therefore, if I'm looking at the coefficient of x equation, ax plus bx better add to 0, which means a plus b better add to 0. With the constants, minus 6a minus 2b is going to have to add to 7. So again, the coefficient of x on the left-hand side is 0. So the coefficient of x on the right-hand side also has to be 0. That means a plus b has to be 0. Since the constant on the left-hand side is 7, then the constants on the right-hand side have to add to 7. So negative 6a minus 2b has to be equal to 7. If I'm using the RREF, I need to have coefficients of a in the first column, then coefficients of b in the second column, and then the third column has to be the equal to constants if I want to use the RREF. Now I'm going to do that. I'm going to go ahead and find the row reduced echelon form of this matrix. Like I said, I'm using my calculator to do that. You can do it by hand as well, but the quickest way is to use your calculator. If you don't know how to use your calculator to do that, I'll have the appendix video that I'll show you how to do that with. So when it's all said and done, I ended up with 1, 0, negative 1.75, and then 0, 1, and then positive 1.75. You can check that on your own. If you plug in negative 1.75 for A and positive 1.75 for B, they do add to 0. And then if you take 6 times negative 1.75 minus 2 times a positive 1.75, you I'm sorry, negative 6. So you do in fact get a positive 7 there if you plug those in. So short of this story is that A has to be negative 1.75 and B has to be a positive 1.75. Again, that's a lot of work, all to just figure out what the A and the B had to be. But now I know that. Now I know that this rational expression that I'm trying to integrate can be, is the same thing, not can be written or is the same thing as a negative 1.75 divided by x minus 2. I think I'll put the negative in the numerator there. Plus a positive 1.75 over x minus 6. And those two individually are very easy to integrate. So the expression that I have here, 7 over x squared minus 8x plus 12, is equal to this one. And this one is easy to integrate. I get negative 1.75 times the natural log of x minus 2. Then I divide by 1. That doesn't do anything. Plus positive 1.75 times the natural log of x minus 6. And again, I divide by 1, but that doesn't do anything. 1 is the coefficient of x. So that's my answer. Now, if you want to write 1.75 as a fraction of 7 over 4, you can do that as well. 1.75 as a fraction is 7 over 4. So if you like fractions better than decimals, go ahead and do that. But the essence of it is just this. Obviously 1.75 as a decimal ends, so that's kind of a nice decimal to deal with. Sometimes if we want to be precise and our fraction is ugly, then we might want to write things as fractions or mixed numbers or whatever you like. Either way is fine with me. Now you'll notice that I put the a over the x minus 2 and the b over the x minus 6. If you would have swapped those out, if you would have put the b over x minus 2 and the a over the x minus 6, then all of this work would have been just done and reversed, and the roles of a and b would have been interchanged, and so the numerical values for a and b would have been interchanged. So regardless of which one you write first, if you put the a over the x minus 2, or if you put the a over the x minus 6, you'll get the exact same answer in the end, just your roles of a and b will be reversed. I wanted to point that out because oftentimes when people go through and solve this, if they factor and they write the x minus 6 first and the x minus 2 second, then their a and b may be flip-flopped from my a and b. In example 3 and example 4, we were factoring a quadratic. In example 5, we have a cubic in the denominator. Our denominator is x to the third minus 4x, and our numerator is still of degree smaller than our denominator, so there's no division necessary. Now, if our denominator is x to the third minus 4x, then we still go about this in the same way, except our denominator is going to factor into 3 linear pieces instead of 2 linear pieces. Let's go ahead and do that. We want to rewrite this rational expression into a piece where, or to multiple pieces where the denominators are linear. That requires us to factor the current denominator. Now, if I factor the current denominator, the first thing I'm going to do is factor out an x. I'll be left with x squared minus 4. That's a difference of squares. So I get x, and then x squared minus 4 factored is an x plus 2 times an x minus 2. Doesn't really matter which one you put in front or what order you have that in, but that's what it is. That factoring tells us that we can rewrite this rational expression into a sum of 3 fractions. All of these are distinct linear pieces, distinct meaning different from each other. So I'm going to take something over a, I'll call that a over x, excuse me, something that's a over x, b over x plus 2. Let me put that in parentheses. And then I'll use a new letter c over x minus 2. This is different than the plus c we'll add on at the very end. So hopefully that doesn't throw you off. I'm not going to write down every single thing in this case, but I want you to notice that if I want a common denominator for this first fraction, I would have to multiply the top and the bottom by both x plus 2 and x minus 2. For this second fraction, I'd have to multiply the top and the bottom by an x and an x minus 2. And for the third fraction, I'd have to multiply both the top and the bottom by both an x and an x plus 2. The numerators is what I'm going to set equal. I'm just going to write that down. I'll write it in the same order. So A times x plus 2 times x minus 2 plus B, I'm going to have to multiply by x and then an x minus 2. Notice it's x minus 2, that's the one that's missing. And then the C, I'm going to have to multiply by an x and an x plus 2. If I multiply that right-hand side out, well, the left-hand side, we'll just leave still. 5x squared minus 12x minus 12. The right-hand side, x plus 2 times x minus 2 would be x squared minus 4. Okay, that's what you get when you take x plus 2 times x minus 2. So I'm going to get an ax squared minus 4a. When I multiply bx times x and then bx times negative 2, I get a bx squared minus 2bx. That's if I distribute. Bx times x is bx squared. Bx times negative 2 is negative 2bx. Cx times x is cx squared. Cx times 2 is a plus 2 cx. Now previously, I had the coefficient of x equation and then the constant equation. Now I'm also going to have a coefficient of x squared equation because obviously I have an x squared. So there we go. So let's look at the x squared terms. Ax squared, bx squared, and cx squared on the right have to combine to give me 5x squared on the left. So that means a plus b plus b plus c on the right have to add to 5 on the left. Coefficient of x. Well, there's no x times a, but there is a minus 2b times x and a plus 2c times x. So I get minus 2b plus 2c on the left-hand side as coefficients of x. And on the right-hand side, the coefficient of x is negative 12. Lastly is my constant equation. On the right-hand side, that term has an x, that term has an x squared, that term has an x, that term has an x squared, that term has an x squared. The only term without an x or an x squared is negative 4a. And then that has to equal to negative 12, has to be equal to negative 12 on the left-hand side constant. This one is not too bad to solve on its own. You can see by that constant equation that a has to be 3. Then you could plug the a of 3 back in and solve for b and the c. But I think I'm going to still use the row reduced echelon form of a matrix. However, because I have 3 equations and I have 3 variables plus a constant, the way my matrix is going to look is it's going to look like a 3 by 3 with another, well, I should say It's going to have 3 rows and 4 columns. The first row, let's put set as my coefficient of x squared equation. I'll write A as the first column, B is the second, C is the third, and then my constant is my last. So I'd get 1, 1, 1. That's A plus B plus C is equal to 5. My second equation, there's no A, so I'll put a 0 as a coefficient there. Negative 2B plus a positive 2C equals a negative 12. And then my last row is going to be from the constant equation, negative 4A plus no B plus no C equals negative 12. And then I'm going to put all of that into my calculator and have my calculator put that in RREF. Again, check out the tutorial video on that if you want to see how that's done. So what we end up with is this really nice matrix. And in the first 3 rows, in the first 3 columns, we get 1s on the diagonal, 0s elsewhere. And then lastly, we get 3, 4, negative 2. And what this means is that the coefficients that we were looking, or excuse me, not the coefficients, but the A, B, and C we were looking for an A which is 3, a B which is 4, and a C which is negative 2. Again, that's a lot of work, but all of that work is going to pay off in my integration. So I go back up here and I say, I know this rational function can be rewritten as A over X plus B over X plus 2 plus C over X minus 2. And now I know that the A that I want is a 3. The B that I wanted was a 4. And the C that I wanted was a negative 2. Now again, when you factored, if you put the A over the X plus 2 and the B over the X and the C over the X minus 2 or the C over the X, and then your A's, B's, and C's would be slightly different, but they'd all give you that same answer in the end. Each of these pieces I can integrate very quickly. The first piece is 3 times the natural log of X. Once again, I'm using parentheses instead of absolute values. Then we go 4 times the natural log of X plus 2. Again, I would be dividing by a positive 1, my coefficient of X, but that doesn't do anything. And then minus 2 times the natural log of X minus 2. And then plus any constant that we want. Again, be careful, this plus C is not the same thing as the value I was using here. If that confuses you, then just use a different letter down here rather than a C. Usually that doesn't confuse people though. So that's what we get. We take a rational expression, we rewrite it into something that's easier to deal with, and then in these pieces I can integrate individually. I do want to mention a couple of things. A lot of times people will rewrite this again using the rules of natural logs. So the rules of natural logs, if you remember, any numerical value out front, you can take this 3 and say that's the same thing as natural log of x cubed. This is the same thing as natural log of x plus 2 to the 4th. This is the same thing as natural log of x minus 2 raised to the negative 2 power. And then when you add natural logs, that's like multiplying the arguments inside. So there's a lot of different ways to rewrite this. If you ask AI to integrate this, or if you ask some specialty software, they might give the answer back in a very different way. They may give the answer, for instance, as, oh, I don't know. Let's do x to the 3rd inside the natural log times x plus 2 raised to the 4th, again inside that argument, and then divided by x minus 2 raised to the 2nd power. And these things, this answer, the one I wrote here, and this answer are equivalent using the rules of natural logs. So natural log of x to the 3rd, natural log of x plus 2 to the 4th. When you add two natural logs, you can multiply the insides. And then a minus, you can either divide, or x minus 2 to the negative 2, you put x minus 2 to the positive 2 in the denominator. So there's lots and lots of different ways to rewrite this. I would suggest most of the time, just keep it simple. Leave it as 3 times natural log of x, 4 times natural log of x plus 2, minus 2 times natural log of x minus 2, and then plus any constant that we want. So there you go. I want you to notice that in these ones that we've been factoring, they've always been factoring into distinct linear pieces. We're going to see what happens if we don't have that property in the next example. Okay, let's integrate this by using partial fractions. We have the rational expression whose numerator is 4x minus 5 and whose denominator is x squared plus 6x plus 9. So 4x minus 5 in the numerator, x squared plus 6x plus 9 in the denominator, and we want to integrate that with respect to x. In this case, our denominator of x squared plus 6x plus 9 factors, but factors into linear pieces that are the same. In other words, we're going to get x plus 3 times another copy of x plus 3. Now, this is not as nice as our previous cases. It's really nice when we have distinct linear factors, but this one's still perfectly fine. I just have to understand what fractions I need to add. Now, if I add fractions, one of which whose denominator is x plus 3, and another of which whose denominator is x plus 3, it doesn't work out nicely because things are ambiguous. The A and the B are going to be ambiguous. So what we do in this case, if we have a repeated linear factor, we write one linear factor raised to the 1st power, and then our second linear factor, we're going to raise that to the 2nd power. Now we're going to put an a over in the numerator of one fraction and a b in the numerator of the other fraction. To get common denominators with this initial fraction, we'd have to multiply by x plus 3 over x plus 3. So that means my numerators, oh, excuse me. So my numerator here of 4x minus 5 is going to be equal to a times the quantity x plus 3. Now, interestingly enough, x plus 3 squared is in fact, like we just said, x plus 3 times x plus 3 is in fact the denominator that we already wanted. So what I've done is I've said this thing is like a real number over x plus 3 plus another real number over x plus 3 squared. Well, x plus 3 squared is already the denominator I want, so I just need b there. I don't have to multiply by anything on top and bottom. That gives me this equation. Numerators, therefore, have to be equal. 4x minus 5 has to be equal to ax plus 3a plus b. There's no x squared equation, but there is an x equation. In this case, notice that there's only one term with an x on the right-hand side. That's ax. And one term with an x on it on the left-hand side, that's 4. So a has to be equal to 4 is what I get from the coefficient of x equation. Excuse me. The constant equation, I have 3a plus b, 3a plus b on the right-hand side. On the left-hand side, I have -5. Now, if we want to do the RREF, we could take, in this case, a 2x3 matrix, take RREF, get another 2. This one is just as easy just to say, well, A has to be 4, and then plug in A. You get 12 plus B has to be -5, so B would have to be 17. But, excuse me, -17. But you could also do the RREF thing as well. The first equation gives you 1 as your coefficient of A, 0 as your coefficient of B, and then 4 as your constant. The second equation gives you 3, 1, -5. When you take that to row reduced echelon form, you get 1, 0, 4, and then you'll get 0, 1, -17. So 3 times 4 minus 17 gives me the -5 that I'm looking for. Now we're ready to integrate. Like I said, because of factoring, I knew what was going to happen. I knew that this rational expression is going to look like a real number over x plus 3 plus another real number over x plus 3 squared. And now I know that the number over the x plus 3 was a 4, and the number over the x plus 3 squared was a -17. Now don't get too much in a rush. This one, 4 over x plus 3, integrates with natural log, but integrates as natural log. But the other one, I'd probably rewrite as negative 17 times x plus 3 to the negative 2 and use my rule of exponents there, meaning raise the exponent by 1 and then divide by the new exponent. So what I would end up with is 4 times natural log of x plus 3 minus 17 times x plus 3. When I raise the exponent by 1, I get a negative 1. And so I'd have to divide by negative 1. So I'd divide that 17 by a negative 1. Now, you're going to see, obviously, you already see, I'm sure, what happens here. Negative 17 over negative 1 becomes a positive 17. And if you want to think of this x plus 3 to the negative 1 in fraction form, that's usually a good thing to do as well. We're going to get 4 times the natural log of x plus 3 plus, if I write it in fraction form, this is going to be a positive 17 divided by x plus 3 to the first power. So just cleaning that up a little bit makes it 4 times natural log of x plus 3 plus 17 over x plus 3 to the first power. So that's how that works. And again, the whole thing hinges upon understanding this rewrite. Understanding that if I have linear factors repeated, then I can do a over the linear factor to the first power plus b over the linear factor to the second power. Let's try another one. We want to integrate the rational expression 2x divided by denominator of x squared minus 14x plus 49. We integrate that with respect to x. If you would like to try this on your own, push pause. After a couple of seconds, I will do the problem on this video. So let's do this. Denominator x squared minus 14x plus 49. That factors into x plus 7. I misspoke here. X squared minus 14x plus 49. Excuse me, I knew something was going on. X minus 7 times another copy of x minus 7. So that means my original rational expression in there can be rewritten as something, some real number over x minus 7 plus some other real number over x minus 7 squared. The first, in order to make the denominators equal, the first fraction, we'd multiply top and bottom by an x minus 7. So we get 2x equals a times on top and bottom x minus 7. Plus the second fraction, I wouldn't have to multiply by anything. So I just get a plus b. So that means 2x is equal to ax minus 7a plus b. And once again, this is a quadratic, so there's no coefficient of x squared equation, but coefficient of x equation, on the right, I have just a. On the left, I have 2, so A has to be 2. The constant equation, well, on the left, the constant is 0. On the right, the constant is negative 7A plus B. Now, if A is 2, it's pretty easy to see that B has to be 14. So if A is 2, B is 14. If you wrote it in this row reduced echelon form, remember, we have to have A's being in the first column. So I do, first equation would be 1A plus no B is equal to 2. In the second column, I'd want to put that 0 on the right-hand side so that I have negative 7A plus 1B is equal to 0. If you do the row reduced echelon form, you get 1, 0, 2 as the first row, and then you get 0, 1, 14 as the second row. So again, A would be equal to 2, and B would be equal to 14. You don't have to always do the row reduced echelon form. I'm just trying to show that and emphasize that if you need it. So if you need it, especially in problems which are more elaborate, then it's nice to have. But on this one, I would have probably just plugged in 2 for A and then solved for B and saw that B was 14. In any case, all this means is that when we integrate 2x over the quantity x squared minus 14x plus 49, that is the same as integrating a over x minus 7 plus b over x minus 7 quantity squared. And again, we saw that a needed to be 2 and b needed to be 14 from our work down here. And that's all being integrated with respect to x. Usually I rewrite this. I know even if some of you can do it in your head, that's perfectly fine if you can do it in your head. 2 over x minus 7 plus 14 times x minus 7 quantity to the negative second power. That to me is easier to integrate. I always like the rewrite. So now we integrate 2 times natural log of x minus 7. I put in parentheses, but a lot of people put those in absolute value. In fact, it's more proper to put those in absolute value, but I know I have to plug in positive numbers into natural log. And then what we're going to get when we add 1 to the exponent, we're going to get x minus 7 to the negative 1. That's going to be x minus 7 in the denominator. Oh, hit the wrong button. X minus 7 in the denominator. It's x minus 7 to the negative 1. Then we divide by negative 1. 14 divided by negative 1 is a negative 14. And then we can tack on any constant that we'd like. So this is our final answer. Again, you can put plus a negative 14. You could put the minus out in front. If you want to call this natural log of x minus 7 squared because you want to take the 2 in and use some powers of natural logs, some power rules on natural logs, you can do that as well. But this is what you end up with. 2 times natural log of x minus 7 minus 14 over x minus 7 plus any constant that we want. That's the antiderivative of this rational function. Let's do another example. Here we have an integration of a rational function. That rational function is x squared plus 3x minus 4 over the polynomial x to the third minus 4x squared plus 4x. So this is a cubic polynomial in the denominator. Obviously, a quadratic in the numerator. You could push pause and think through how you would factor this and then how you would set up the smaller fractions that you want to break this into. So I'll give you a couple of seconds there and then I'll do it on my own. So if you want to try it, obviously, hopefully you've pushed pause, work it out on your own, but I'm going to try it. I'm going to do it on my own now. So we got x to the third minus 4x squared plus 4x. The first thing I'm going to do is factor out an x. That'll leave x squared minus 4x plus 4. That x squared minus 4x plus 4 breaks down into x plus, excuse me, not x plus, x minus 2 times another copy of x minus 2. So I get some factors. I get a pair of repeats and one that's distinct from the rest. It may be obvious to some, it may be very unobvious to others of how to put these together. Basically, what you're going to do is you're going to put x, the distinct one, as one denominator, then x minus 2, the second distinct one, as the second denominator, and then x minus 2 squared, or x minus 2 times another copy of x minus 2, as the third denominator. Now, you don't have to put them in that order, but you need all three of these. So if you wanted to put the a over the x minus 2 and the b over the x minus 2 squared, by all means, you can do that. Whoops. So we get these three fractions, and whichever one you want to put the numerator of a on, that's fine. Whichever one you want to put the numerator of b on, that's fine. Whichever one you want to put the numerator of c on, that's fine. So we have three fractions, and now I would want to make sure the numerators match up. Now, if I'm forcing numerators to match up, that means I'm forcing common denominators. What a would have to do, this fraction a over x, to get a common denominator, a would have to multiply by x minus 2 times another copy of x minus 2. So this first fraction, we need to multiply top and bottom by x minus 2 squared. The second fraction, the b on top and bottom, would have to multiply times one copy of x and one copy of x minus 2. Because we already have one copy. We need a copy of x minus 2, another copy of x minus 2, and a copy of x to get a common denominator. I think I'm going to do it that way. And for my last fraction, this c would have to multiply times x, and I would have to multiply x by top and bottom to get common denominators. So if I took a times x minus 2 squared, I'd get x minus 2 squared on top and bottom. I'd get that. B times x minus 2. I'd get that as my numerator. C times x would give me that as my numerator. I'll multiply this out. X minus 2 squared is x squared minus 4x plus 4. When I multiply a times everything, actually, let me go ahead and I'll do another line. When I multiply this x, this x times 2, I get b times x squared minus 2x. And then obviously plus cx, I don't have to do anything with that. So the numerators, we're getting x squared plus 3x minus 4 on the left-hand side. The right-hand side, I have ax squared minus 4 times ax plus 4 times a plus bx squared minus 2 times b times x plus c times x. Oops, that's a lowercase. I should have put a capital. There we go. Hopefully that makes sense. Now, the coefficient of x squared equation. We have ax squared and bx squared on the right. There's no cx squared, just cx. So a plus b is going to have to be equal to 1 since ax squared plus bx squared has to be equal to x squared. So a plus b has to be 1. As far as the coefficient of x's go, we have negative 4a times x minus 2b times x plus c times x. Those are all the x terms. Negative 4ax minus 2bx plus cx has to add to the other side, which is 3x. So has to add to 3. So negative 4a minus 2b plus c has to be equal to 3. My constant equation, on the left we have negative 4. The only constant here is 4a. So we get 4a equals negative 4. This one you can actually do pretty quickly. A is negative 1, plug that in. B is 2, plug in those two and find your C. So you can do this by hand really quickly if you want. You can also use the row reduced echelon form. The first equation gives you 1, 1, 0 equals 1. 1a plus 1b plus 0c equals 1. The second equation tells you negative 4a minus 2b plus 1c has to add to give you 3. And then the last equation says 4a plus 0b plus 0c has to be equal to negative 4. So whether you want to just use some logic or use RREF, either way is good to go. Again, if you just want to use straightforward logic and substitution, this last equation gives me an a of negative 1. When I plug in negative 1 here, add 1 to both sides, you get b is 2. And then if A is -1 and B is 2, that would mean C has to be 3 from this middle equation. But you can also check that by doing RREF of this matrix. If you did do RREF of that matrix, the first 3 by 3 piece would give you zeros and then ones on the diagonal, and then you would get -1, 2, and 3 as your last column. So we're saying A is -1, B is 2, and C is 3. So a long process in order to get the A, B, and C correct. But now that we have the A, B, and C correct, we can say our original integration was the same as integrating A over X plus B over X minus 2 plus C over X minus 2 quantity squared with respect to X. And now we know that A here should have been -1, B here would have been 2, and C here would have been 3. Once you've done things like this last term a lot, then you can do it all in your head. I'll do this one in my head. -1 over X, that's negative natural log of X. Again, probably should use absolute values there. I just wrote it in parentheses because that's easier to type. 2 times the natural log of X minus 2 is what you get with the second term. Again, I would divide by 1 as my coefficient of X, but that doesn't do anything. And then, oops. What you would do is you'd call this thing X plus 2 to the -2. When you add 1, you'd get X minus 2, X minus 2 to the -2. You get X minus 2 to the first power in the denominator. And then you'd have to divide by -1. Dividing by -1 would turn that 3 into a -3. And you can rewrite it as plus a -3 or -3 over X minus 2. And then, like always, we tack on any constant that we want. So we tack on any plus C that we like. Again, that plus C is different than this C. This C was the number I was looking for, but this C is just some arbitrary constant of C. If that throws you off, use a different letter down here. But that's the final answer. So the final answer is negative natural log of X plus 2 times the natural log of X minus 2 minus 3 over X minus 2 plus a constant. And the key part there was how we broke it up. So breaking this up into A over X, that's a distinct piece. X minus 2, that's another distinct. And then I have another copy of X minus 2, so I go X minus 2 squared in the denominator. So that factoring and that breaking up was the key part. That's kind of combining examples 3, 4, 5, 6, 7 there, those ideas. Now let's do another example here where we want to integrate using partial fractions. In this case, I've already factored the denominator. I've factored it into X minus 1 times x squared plus 1. And the numerator is going to be an x plus 3. So I want to integrate this rational fraction whose numerator is x plus 3 and whose denominator is x minus 1 times x squared plus 1. If we want to break this down, we have to do it in a different way than what we've done before. The reason is when I go to factor this denominator, the x minus 1 is its own linear piece. But the x squared plus 1 does not factor over the real numbers. If I could factor it over the real numbers, I would here. Even if it were ugly real numbers, I'd go ahead and do it. But x squared plus 1 does not factor over the real numbers. It actually factors only over the complex numbers. When I want to integrate, that's not very nice to use complex numbers. So I have to leave this as x squared plus 1 because it doesn't factor over the real numbers. And that kind of is a little bit, that stinks a little bit because that means one denominator is going to be x minus 1 and the other denominator is going to be quadratic. And I don't like quadratic pieces. Well, at least I don't yet. So here's what I do. A linear distinct piece, I just put a real number on top. If I have a quadratic piece, what I have to do is I have to put a linear piece on top. Just a fact that I want to mention here is that if I start with a if I start with a polynomial over the real numbers, it will always break into linear and quadratic terms over the real numbers. So if I do need a quadratic, if I do need this, I don't ever have to do this with a cubic because I can always break down a cubic. But quadratic, I might not be able to. So in order to get a common denominator, for this first fraction, I'd have to multiply top and bottom by x squared plus 1. So I'd take the a and I'd multiply that by x squared plus 1, and then obviously the denominator I'd multiply by x squared plus 1 too. So top and bottom of this first fraction by x squared plus 1. And then I'd have to take bx plus c, and on the top and bottom of this fraction, I'd have to multiply by x minus 1. Be careful when you do that. You have to do a distribute. This is multiplying two polynomials. So you have to distribute. The left-hand side numerator becomes x plus 3. That's what it always was. The right-hand side numerator would become ax squared plus 1a plus we get bx squared minus bx plus cx minus c. When it's all multiplied through. The coefficient of x squared, I have a plus b on the right-hand side. And on the left-hand side, I don't have any x squared, so that's just a 0. The coefficient of x. Well, I have minus bx plus cx. So coefficient of x is going to be negative b plus c. And then equal to 1 on that side. For the constant equation, I'd have a minus c on the right-hand side, and I'd have equal to 3 on the left-hand side. So when I write that down, again, I usually use, if I'm using RREF, I like to write the constants on the right and my variable pieces on the left. Now, this one, again, you can do by hand. It turns out if you add all three equations together, the b's will cancel out, the c's will cancel out. You'll be left with 2a is equal to 4. So that means a is 2. If a is 2, then based on this, a plus b having to equal 0, b would have to be negative 2. And if a is 2, then this last equation means that c has to be negative 1. You could have also plugged in negative 2 here, and then saw c has to be negative 1 in the second equation as well. But basically, if that's what you get if you do it by hand, if you did it by using the RREF, you do 1, 1, 0, 0. A plus B plus 0C equals 0. 0A minus 1B plus 1C would have to be equal to 1. That's the second equation. And then 1A, 0B, negative 1C is equal to 3. That's the third equation. And then you'll get the standard RREF. It takes longer to type in than anything. And the RREF would say A is equal to 2, B is equal to negative 2, C is equal to negative 1. So that's what we get. So what that means is that this rational expression is the same thing as this rational expression, where A is 2, right? A is 2, B is negative 2, C is negative 1. Now, this first fraction is easy to deal with. This second fraction, it takes a little bit more algebraic work. So it's not terribly hard. So I'll go ahead and do it this time. Actually, what you would do is you would, in this case, and I only know this because I've done this before, you'd break it into these three pieces, okay? And then I integrate each of those three pieces. Now, I'm going to integrate those three pieces separately. So if I integrate 2 over x minus 1, I know how to do that. That's going to be using natural log. Then I'm going to integrate negative 2x over x squared plus 1. That's going to be easy using just a standard u substitution. And then I'm going to integrate negative 1 over x squared plus 1. That is what we do with a trig substitution. We use a trig substitution for that. In fact, we've done this one before. This one is the one that's going to be the most difficult. So just again, u is going to be equal to x squared plus 1. Then my du dx exchange, du is going to be equal to 2x, and then multiply. So 2x dx. So notice what we get is 1 du over u. So I'm going to get negative the natural log of u, which is x squared plus 1. So I'm going to write that down, sorry. So now that we've integrated, I'll integrate this first piece. That first piece is going to be 2 times the natural log of x minus 1. I'm arguing that this second piece, with just a simple u substitution on this middle piece, we get negative natural log of u, and our u is x squared plus 1. So negative natural log of u, and then replace the u with an x squared plus 1. I don't have to even put absolute values because x squared plus 1 is always going to be positive. And then this last one, well, that is going to be more complex. That's going to be done using a trig substitution. However, we actually already did this in the last section. We did this exact same integration in the last section. So let me just remind you of that. In example 9, in the last section, we found that when we integrated 1 over x squared plus 1, we got the arctangent of x, or the inverse tangent of x, obviously plus any constant that we want. So if you want to go back and look at where that came from, go back to the trig substitution section. But we ended up with arctan in example 9 of that last section. So that means this third integration is simply minus the arctangent of x. And then obviously we always have to tack on plus any constant that we want. Once again, there's a lot of different ways to rewrite these first couple of natural logs, but I always, if I can, keep it as simple as possible. So first one is just a standard natural log integration. Second one is a u substitution integration. Third one is a trig substitution, and you get arctangent, or the inverse tangent if you'd rather write it as inverse tangent. But there you go. Again, key thing there was that with the factoring, when we had a quadratic that we couldn't factor, we put a linear as our numerator and the quadratic as our denominator. And with the linear piece, we need a coefficient to the x and a coefficient of the constant. Now we can do lots and lots of really tough fractions and tough rational expression breakdowns if we want. So we're not going to go through the entire solving process in these next couple of examples. Instead, let's just focus on how we would break the fraction up if we wanted to integrate using partial fractions. So what if we had this, and x squared plus 2 times another copy of x squared plus 2 in the denominator? X squared plus 2 as a quadratic does not factor over the real numbers. It's also imaginary. So it factors over the complex numbers, but doesn't factor over the real numbers. But we also have 2 copies of them. So what would we do if we had 2 of the identical copies of quadratics that did not factor? Again, this is like a combination of the previous example, that's example 9, with repeated factors. So what would happen is you would set this up as first denominator is x squared plus 2. And since we have a repeated factor, the second denominator would be x squared plus 2, quantity squared. What would the numerators be? Well, the numerator in the first one would have to be a linear piece, so something like ax plus b. And in the second one, it would also be a linear piece. It would be something like cx plus d. You can imagine that this would be fairly cumbersome to figure out the a, the b, the c, and the d. You can use matrices and row-reduced echelon form of matrices to do that. That makes your life a lot easier, but it's still fairly cumbersome. So that's the breakdown, and I'll just leave it at that. We won't go through solving this entire problem. Let's do another. Let's take and let's say we want to integrate this rational expression, 3x squared minus 6x plus 13, over, in the denominator, we have x plus 3, we have x minus 4, quantity squared, and we have an x squared plus 18. That x squared plus 18 is a quadratic that does not factor over the real numbers. So let's think about what the fraction structure would be. We're not going to solve this whole thing. We're just going to set up the fraction structure. Try to do this on your own if you want by push pause on the video, because on the video, I'm only going to give a couple of seconds, but you probably need longer than that to solve on your own. All right, so let's do the breakdown. We have one linear factor that's not repeated of x plus 3. So that's going to be an a over an x plus 3. That's going to give me that type of a fraction in my breakdown. Then I have 2 copies of x minus 4. So I'm going to get a b over an x minus 4. And then I'm going to get a c over an x minus 4 quantity squared. So since there's 2 copies of that, I'll do that. By the way, if there was a third copy, I'd have to do a d over an x minus 4 to the third power. So in this case, the last part of the denominator, the last factor, is a quadratic that does not factor over the real numbers. So that gives me an x squared plus 18 in the denominator. Since that is a quadratic, I'd have a dx plus e, or I'd have a linear piece in the numerator. So that's my breakdown. Again, a over x plus 3 plus b over x minus 4 plus c over x minus 4 squared plus dx plus e divided by x squared plus 18. So that's the entire breakdown. And then you'd have to solve for A, B, C, D, and E. That would be a very cumbersome process. It's very doable. It just takes a while. And then you'd have to integrate each piece individually. So that's the basics of how to set up and use partial fractions here. Again, I know I didn't give any examples, but if you did have an x minus 4 raised to the third, then what you would have done is you would have just added another fraction of x minus 4 to the third power. You'd have put a d over there, and then that coefficient would have become an e, and that coefficient would become an f. And again, it doesn't matter the order you write these in. You could have swapped up any of these letters and swapped up the order for any of those letters. I just added 2 there, so I'll leave what I have. Again, it'd take a long time to set up all of our equations. We'd have an equation for an x to the fourth, an equation for an x to the third, an equation for an x squared, an equation for an x, equation for a constant, and then we'd have to solve them all. So there we go. So that being said, something like this example, like example 11, you probably wouldn't get on a homework problem to do completely. You could get what's the breakdown, but you may get something like example 7 or example 4 on your homework. Those are pretty, example 3, those are pretty standard partial fraction type problems. And like I said, don't forget, from example 3 and beyond, we always started with denominator higher degree than our numerator. The reason we did that is because if we ever start with a higher degree or equal degree in our numerator, then we can divide and get polynomial piece plus rational piece. And the rational piece is what I'd have to use my partial fractions technique on. So that's the idea of partial fractions. And that ends this section.